Another one with all these nice little ratios. Now we're actually moving into an old A-level question. 2014 Unit 5 was in the A-level. Ammonium chloride and sodium nitrite react together in aqueous solution to produce nitrogen gas. So here's the net ionic equation. There's the ammonium. Don't worry about the chloride, it's a spectator ion. There's the nitrite, don't worry about the sodium, it's a spectator ion, giving us N2 and H2O. Tells us that the rate equation is rate is K times concentration of NH4 plus times the concentration of nitrite. Okay, and now it wants to complete data for the above reaction. Well, we're going to use the fact that we know that it's first order in ammonium, so whatever we do to the ammonium, we do to the rate. And it's first order in nitrite, so whatever we do to the nitrite, we do to the rate. So let's fill in these gaps here, shall we? Looking first of all for experiment 1 and 2, as we go from 1 to 2, the rate halves. Well, nothing happened to the nitrite, so that means it must have to do with the ammonium. And whatever we do to the ammonium, we do to the rate. So the converse of that is whatever happened to the rate was due to the ammonium. So we halve the rate. So we're going to halve the ammonium. So that's 0.1. Okay. Now let's think about number 3. Okay. What happened with number 3? Well, the rate went up by a factor of 6. Okay. The ammonium only went up by a factor of 2. So somehow we must have another factor of 3 to worry about. Well, that obviously comes from the nitrite. Okay, if that's times 2 and the whole thing's times 6, this must be times 3. So that means that the nitrite wasn't 0.101, it was 0.03. And then finally, this one here, how do we compare to experiment 4 to get the rate? Well, various things we could do. I would look at 2 and 4. As I go 2 to 4, the ammonium stays the same, 0.1 and 0.1. The nitrite doubles, 0.01 to 0.02. Whatever happens to the nitrite happens to the rate, thus the rate must also double, thus 4 times 10 to the 7 moles per cubic decimeter per second. That was kind of fun and also produced a very nice pretty picture, didn't it? Right, so there's the table with our data in. Calculate the value of the rate constant K given its units. Well, let's see, we know the rate, we know K, the ammonium, we know the nitrite, so the only thing we don't know is K. So I'm going to rearrange this equation here to give me K all by itself. So I'm going to take the rate and divide it by NH4 plus times NO2 minus, just essentially taking both of these over to that side to give me K all by itself. And now pop in the numbers. When I do it for the first experiment, I get K as 2 times 10 to the minus 4, right? Rate, 4 times 10 to the minus 7, divided by the ammonium, 0.2, divided by the nitrite, 0.01. Punch all that into our trusty calculators, 2 times 10 to the minus 4. Do the same thing for the data for experiment 2, for experiment 3, and for experiment 4. Always do it for as many as you can, as many of the sets of experiments as you can, because K should be the same for all of them. And it's a great double check that you did the calculations previously correctly. What we find here is K, as we were hoping / expecting, is the same in all. Thus K is 2 times 10 to the minus 4. And the units of this, well, it is a second order reaction overall. First order and first order gives us second overall. Units for the rate constant for a second order reaction as moles per mole per cubic decimeter cubed per mole per second. Sorry about that. I should have written it the other way around. Decimeter cubed per mole per second. How does the value of K alter if the concentration of H4 plus ions is increased? Well, the whole point of the rate constant of K, it's pretty lousy constant because it changes with temperature, but at a given temperature, it is independent of concentration. So thus, it will not change with concentration, but if you increase the temperature, K will increase. That actually comes, of course, from the Arrhenius equation, but generally the way you can say it at this level is when you increase the temperature, all reactions speed up, so the rate increases, and that is where K changes, because the rate is, of course, proportional to K for a given set of concentrations. Now the clock reaction, that's the hydrogen peroxide reaction with acidified, that's the H+, potassium iodide, that's the I-. The potassium is the spectator ion, so we don't include it, and whatever the counter ion was with the H+, we don't include. So studied using iodine clock reaction, discussed the principles, how the rate is determined, experiment details not required. So what you do with a clock reaction is you first of all have to have a coloured product. In this case that's the iodine. Now thus, as the reaction happens, you start making iodine, and under normal conditions it just gets a little bit yellow and then a bit yellower and darker yellow and light brown and dark brown as the iodine is produced. But what you do to make it a clock reaction instead of just a reaction that gradually turns brown is you put another species in there that's going to react quickly with that particular product, with the iodine. Usually you throw in some thiosulfate, S2O3 2-. S2O3 2- loves iodine. So as soon as you make a bit of iodine, the thiosulfate snags it up, no colour. Make a bit more iodine, thiosulfate snags it up, no colour. Make a bit more iodine, thiosulfate snags it up, no colour. And then once that thiosulfate is used up, then the next little bit of iodine that's made, boom, you get some colour. Okay, so the whole idea of the clock reaction is that you delay production of the colour, right, by a certain length of time depending on how much of that added species you use. And then the way you determine the rate is you just measure the time taken for that color change, and then 1 over that is the rate of the reaction. If you want to get particularly good, you can include the concentration of the thiosulfate, because that's what's changing to give you that color change. Here's a nice little table for experiments, changing the H2O2 concentration, changing the I- concentration, and changing the H+ concentration by changing the pH. So it wants to know about the pH, pH 1, pH 2. Well, if the pH is 1, pH is minus the log of the H+, so minus the log of the H+ is 1. So log of the H+ is minus 1, so therefore H+ is 0.1. Plug it in your calculator, take 10 to the x, it gets rid of the log, and 10 to the minus 1 is 0.1. Do the same thing for the pH 2. The H+ concentration 0.01. So a 1 change in pH is actually a 10-fold difference in the H+ concentration. Same question, same data, expanded table to allow us to see it better, and we're asked to deduce the rate equation, or the rate law. So what we're going to do is we're going to find pairs of experiments in which only one variable of the H2O2, the I- or the pH, has been changed. So if I look at 1 versus 2, we've changed the H2O2, goes from 0.01 to 0.002, so it's doubled. The I- is the same, the pH is the same, the rate has doubled. Thus, the rate is proportional to the H2O2 to the 1. Whatever we do to the H2O2, we do to the rate. Now let's think about, what should we look for now? Maybe equations 2 and 3. The H2O2 the same, the I- the same, but the pH has changed. Now it looks like it's doubled, but remember what we just calculated, the difference between those is to the power of 10. Okay, this is 1/10 the pH of that one. Well, what effect does that have on the rate? Absolutely nothing. So in other words, the rate does not depend upon the H+. We can mess around with the pH all we want. Won't affect the rate. The rate is proportional to the H+ to the power of 0. And finally, we want the I-. Well, what should we compare for the I-? How about 1 and 4? 1 and 4, the H2O2 doesn't change. The pH doesn't change, although quite frankly, we don't care if it does because it doesn't do anything. And the I- goes from 0.1 to 0.4, so that's a factor of 4. What does that do to the rate? 2.8 up to 11.2, also a factor of 4. So thus from that, the rate is proportional to the concentration of I-. Okay, put it all together. Rate is K times IH2O2 to the 1 times I- to the 1, and the H+ is not involved in the slow step, which of course we define later in the A-level curriculum. Calculate the value of the rate constant given the units. Well, I always like to rearrange it so that now I've got K as rate divided by the H2O2 times the I minus. So now let's calculate K. Let's do it here, as that's where we got some space. So throwing in for equation 1, we'll take the rate, 2.8 times 10 to the minus 6, divide it by 0.001, divide it by 0.1, and we get 0.028. Do the same for equations 2, reaction 3, reaction 4. Again, do it as many times as you can to double check your work. Put it all together, and K 0.028 decimeters cubed per mole per second. Equations repeat at high temperature. How does temperature increase affect the rate equation and the rate constant? Well, the important thing is that the rate constant is constant at a given temperature, but increase the temperature, you increase the rate constant. But what is constant throughout are the orders of the reaction. The orders will only change when the mechanism changes. So the increase in temperature, assuming it doesn't affect the actual mechanism of the reaction, will have zero effect on the orders on the rate equation. Question 10 I thought was a clever one. Iodomethane reacting with thiosulfate, range of temperatures, first order in iodomethane, so there we are, and a rate constant 3.1 per mole cubic decimeter per second. Now that's telling us it's a second order reaction. Well, if it's first order in the CH3I, it must therefore be first order in the thiosulfate. So that's the rate equation. Rate is K times concentration CH3I times the concentration of S2O3 2 minus. Ellen carried out investigation rate of reaction between propanone and iodine. Yes, propanone, otherwise known as acetone, and iodine in acidic solution. First part of the investigation, she measured the concentration of propanone. That's the concentration of propanone. Changed with time. Results shown in the graph. Explain how the graph shows the reaction is first order with respect to propanone. Unfortunately, of course, at the A level, you don't learn the real way to demonstrate this. So we're just going to fudge it. I'm going to fudge it in two ways. First thing I'm going to do is I'm just going to point out that if we start at 64, that's at 20 seconds, and then we halve that to 32, that's 40 seconds. And then we halve from 32 to 16, and that goes from 40 to 60. And then we halve from 16 to 8, and it goes from 60 to 80. So each halving has the same time of 20 seconds. So the constant half-life throughout the reaction is a feature of a first order reaction. If it was anything else, then we would have seen different times to go between 64 and 32 compared to 32 and 16 compared to 16 and 8. Now we can actually demonstrate that in a tacky way by looking at the average rates in 20 seconds. Okay, so we'll start with 64 and then we will go another 20 seconds and that gives us 32. Okay, so the rate is 32 over 20, which is 1.6 cubic decimeters per mole per second. Now, let's start at 32. So we're halving the concentration. The rate to go for another 20 seconds from 32 at 40 seconds to 60 goes from 32 down to 16. So 16 over 20, so 0.8 cubic decimeters per mole per second. So we halve the starting concentration, we halve the rate. Let's again start at 16, right, and go another 20 seconds. We go from 16 to 8. So the rate, therefore, we've used up 8 in that 20 seconds, so the rate is 0.4. So again, halve the concentration, halve the rate. It's all going to be first order. Okay, so first order, either way to see that. Go and look at the extension material for the kinetics and look at the integrated rate laws and see how you would properly show that this was first order. So the next part of the experiment, she wanted to mess around with iodine and acid. So here's the change in the iodine concentrations, the change in the acid concentrations, keeping the propanone constant because she knows already that the propanone is first order. So let's compare these things. Let's start off with, well, let's find for the iodine a couple of experiments where we changed the iodine but we left the H plus and of course the propanone the same, and obviously we're going to go with second and third one, right? Relationship between the iodine is 2, the H plus stays the same. Unfortunately, so does the rate. So in other words, the rate has got nothing to do with the iodine concentration. It is 0 order. Now let's do the same thing for the H plus. Let's find 2 experiments where the H plus changes, but the iodine doesn't, even though, of course, we don't care about the iodine anymore, as it's 0 order. But anyway, if we take 1 and 2, or even 1 and 3 there, the H plus doubles. As the H plus doubles, so does the rate. So therefore, whatever the H plus does, the rate does too. The rate is proportional to the H plus, thus it is first order. Right, the rate equation, well, we just stick all that together. Rate is K times the H plus that we found out here, ignoring the I2, and we already knew it was first order from the propanone from the previous experiment. Calculate the value of the rate constant, status unit, well, it's second order, so we know it's going to be cubic decimeters per mole per Kelvin. Now, how do we get K? Well, we take this equation and rearrange it. So K is the rate divided by the concentration terms. Now we'll just pop those values in and calculate it. So 2.1 times 10 to the minus 9 divided by 1.5 times 10 to the minus 3 divided by 0.02 is 7 times 10 to the minus 5. Same thing and same thing. So the rate, 7 times 10 to the minus 5 cubic decimeters per mole per second. Considering the reaction VO2 plus BrO3 minus goes to VO2 plus, so some nice vanadium chemistry, plus Br2 in acidic conditions. The effect of the concentration of H plus ions on the rate of this reaction studied using the same concentration and volumes of everything else. Following data were collected. Find the order reaction with respect to H plus. So here's our pH, there's the rate. So what we got to do is see what the relationship is to this, not to the pH, but to the H plus. So the first thing to do then is let's calculate the H plus. Of course, pH is minus the log of the H plus. So the H plus is 10 to the power of minus the pH. Pop all that in the calculator and we find this. Now let's compare values. So if we look at 1 and 2, the difference between them is 2.5, 0.04 to 0.1 goes up 2.5. And let's compare the rates here. 1.308 to 3.287 is 2.5. 2.51 was 0.01 between friends. So that would imply proportional. But we've got more than one set of data, so always check ourselves. Let's look at these ones. Another nice little easy times 2.5, going from 0.016 to 0.04. What's the relationship going from 5.19 times 10 to the minus 4 to 1.308 times 10 to the minus 3? Again, it's that nice 2.5. And so again, that indicates rate is proportional to the H plus to the 1. So first order for the H plus. So different reaction, but same type of question. Tin ions, so there's the tin 2 plus, Fe3 plus ions, there's the Fe3 plus in acidic solution. So we got pH in here as well. Find the rate equation. Well, the first thing to do is, of course, we don't want pH here. We want the concentration of H plus. pH of 0, very unlikely, but the concentration of H plus is 1. pH of 1, the concentration of H plus is 0.1, as we've seen in a previous question. Now we're set up to compare. So what we want to do is we want to find 2 equations where we can eliminate as much as possible, leaving just one variable behind. So I might start with 3 and 4. 3 and 4, the Fe3 plus the same. The tin is doubled, the H plus the same. What happens to the rate? We go from 1.4 to 2.8. So the rate doubles as well. So this tells us rate is proportional to tin 2 plus. Let's find another couple of ones in which we can eliminate all but one unknown. About 1 and 2. Comparing 1 and 2, we are going from 0.2 to 0.3 in Fe3 plus. The H plus is staying the same. The Sn is doubling, but then of course we know what the effect of doubling the Sn is. That doubles the rate. So anyway, let's have a look here, shall we? We double the Sn2 plus, 1.5, the Fe3 plus. we double the rate. Well, doubling the rate comes from doubling the SN2 plus. In other words, the FE3 plus did absolutely nothing for us whatsoever. So the FE3 plus, pretty as it might be and fun as it might be, doesn't affect the rate of the reaction. And then finally, let's compare 3 and 1, because 3 and 1, the tin 2 plus is the same. Even though, of course, we know what tin 2 plus does, it is proportional, but we might as well keep things as simple as possible. But when we look from 3 to 1, the H plus is a factor of tenfold. And what does this do to the rate? Well, it goes from 1.4 to 1.4. Nope, it goes from 1.4 times 10 to the minus 3 to 1.4 times 10 to the minus 2. So that also is a tenfold increase. So the rate is proportional to the H plus. Thus the rate law, K times the H plus times the tin 2 plus, nothing to do with the iron 3 plus. Value of K, as usual, we've done this a whole bunch now. K is rate divided by the H plus times the SN2 plus. Various values, equation 1, 1.4 times 10 to the minus 2 divided by 1 divided by 0.2 is equal to 0.14. Equation 2, 2.8 times 10 to the minus 2 divided by 1 divided by 0.2 is 0.14. Equation 3, 1.4 times 10 to the minus 3 divided by 0.1 divided by 0.1 is 0.14. And equation 4, also 0.14. Put all those together and the average is 0.14. Again, it is a second order reaction, so the unit rate constant, cubic decimeters per mole per second.